the record. Mark down the time. All right, we're at 10:06. All right. Then I will write this down. Number one from a review. Okay. Now I guess I need to find that. Let's see. So that should be with the solution page, right? Okay. And then exam number 4 review. I think this is what you're asking about, right? Consider two initial frames, S and S prime, where S prime is moving to the right.
Yeah, that's the one.
Okay, perfect. Actually, let me turn up my sound. Here we go. So I can hear you guys. All right, good. I'll read that one, but let me go to then share my screen. And then we get the camera going. Alrighty. All right. How's this modern physics stuff going for you guys? It's different, isn't it?
Yeah, I think the hardest thing for me is knowing which velocity is supposed to be which item.
Oh, yeah. Oh, that reminds me. I'm going to grab my textbook and bring it kind of close here because there's a lot of different equations that have different forms. And, of course, we derive them in lecture, but I don't think we want to go through and rederive them here in our discussion. We probably want to start with that equations. But yeah, I mean, I'm glad you said exactly what you said because there are three speeds that easily get mixed, and I guess I want to kind of emphasize that. So let me read this one here. All right, so considering two initial frames, an S and an S prime. So the tradition, and it doesn't matter which one you call which. I guess that's probably the good news. But one of them, we label everything with a primed, and one of them without a prime. And so I'll just kind of put as viewed by the unprimed system. So we have an S for the system. And so the system would measure things in terms of X and Y. There wouldn't be any primes on them. And the other person would measure position of X prime and Y prime. So everything either has a prime or an unprimed. Okay. And so here's our two systems. And they say that the S prime system is moving at a constant speed of 0.6c as measured by the observer S. All right. So it's impossible. This is hopefully what you got out of the relativity. It's impossible to say one is stationary and one isn't. Everything is just moving relative to each other. A good example, since we drive in automobiles a lot, is kind of like you know well, an automobile, and if you're the driver and you look over at your passenger, you're going to say, hey, my passenger is not moving. From my perspective, my passenger has no motion. My passenger is 2 feet away, and then a little bit later they're still 2 feet away. There's no relative velocity to me. But somebody somewhere else, and maybe standing on the edge of the freeway as you go driving by, is going to say, no, that passenger went whizzing by at 70 miles an hour, and the position is changing. And so all of this is a perspective of what we call relative. What do you see from your perspective? And it's very natural for us to kind of assume there's like this absolute not moving. We like to say, okay, well, the whole reason the passenger doesn't look like the passenger is moving because the driver is also moving. And that's true relative to the ground. But that's just because you're picking the ground. If you were to pick, the inside of the car as kind of your reference point, you would say, no, I'm not moving. Actually, what's happening is the person on the outside, the whole ground, the whole freeway, they're all moving towards me. Anyways, so know this, that it doesn't matter which you call S or S prime, but once you make a decision, you have to be consistent in it. And so the formulas we have, and one of them is V. V is, and I think this is part of where your question is going, Andrew, of okay, how do I keep these symbols straight? V is the symbol that we give for how fast is S prime moving as seen by S. Okay. And so they make it very clear that S prime is moving to the right. So that'd be a positive motion with a constant speed of 0.6 c. So that's the V in all of these equations that we're going to be working with. Okay. Now, a stick of proper length, 1 meter, moves to the left towards the origins of both S and S prime. Okay, so maybe I'll put a stick here in my picture and moving that way. Moving to the left, moving towards the origin. So if it's moving towards the origin, and it says for both of them, then I know it's moving in the negative direction for both of them, although its position is positive. I don't know if that is going to really matter. Most of these, it's just what is their velocity, not necessarily what's their position. But the way it's described, I'm hearing that a stick of proper length, 1 meter, okay, when we'll talk about proper length, moves towards, okay, wait, 1 meter moves to the left towards the origin of both S and S prime. And the length of the stick is 50 centimeters as measured by the observer in S prime. Determine the speed of the stick as measured by the observer S in S prime. Okay, now the part of it where they give me the proper length is a phrase that we kind of coin here that, again, when things are moving, they look different. And the fact that the speeds look different for different people. Let me go back to my discussion about, somebody driving and somebody on the side of the road looking at the passenger. That doesn't surprise us when we say the different observers, the driver and the person on the side of the road, see different speeds. I think what surprises us, though, because we never had this until we got into modern physics, that also the length of an object would look different. And that's what I called, I think, bizarre consequence number 2 in the lecture. It's like, wait a minute, you tell me the actual length of something looks different? And I'm saying, yeah. So just like speeds can be viewed different, length does. And we can review the logic behind that too. But let me take that as a statement. Okay, so this is what we say. We like to say then that the length as observed by somebody in a non-proper reference frame would take the proper length and divide it by this gamma factor. Okay, so what is proper length? So proper length is the length you would measure if you are essentially not moving relative to it. Okay, so when they tell me that the proper length is 1 meter, they would be saying that if somebody was standing on it or something, moving along with it. I got to be careful with that moving, because moving relative to what? Okay, so in other words, a person who would be stationary or moving, however you want to put it, with the meter stick, and I'll call it a meter stick since it's 1 meter long. Okay. That is what that person would observe. Now, according to this description, this meter stick is moving relative to both S prime and S. So both S and S prime would see something smaller. We call this length contraction. Okay, so we know we're going to see something smaller, and that how much smaller depends upon its speed. And the little chart I like to give looks like this. That here is the proper length of it, and then you can look at its length in some other non-proper reference frame. And for our discussion, let me call that S prime. The ultimate question here is to determine the speed of the meter stick as seen in the S one. And I guess there's a couple, I see two ways we might want to get there. And one looks easier than the other. So we'll go the easy direction here. But what I am trying to say here is they gave me both of these in the problem. They said, let me just make sure I'm reading it right. It says the length of the stick is 50 centimeters as measured by the observer in S prime. So I'm going to put here 0.5 meters. We know if you were moving with the meter stick, so there's no motion between you and the meter stick, you would get 1 meter. So rearranging this, we're talking about a gamma factor of 2. And gamma is related to its speed. I like to usually square gamma first. So gamma squared is 4. Because gamma squared is 1 over v squared over c squared equals 2, and this is 4. And so now I guess if I cross multiply, that's a 1, and this would become a 4 minus 4 b squared over c squared. I'll bring this over to here. Maybe I shouldn't do too well. I'm going to do a big step here. I'm bringing a 1 over to there. That's a 3. When I bring this over and then divide by the 4, I get v squared over c squared. So finally, for v, I get the square root of 3/4 times c, which is root 3 over 2c, which if I convert that to a decimal, the square root of 3 divided by 2 is 0.8. And I should put plus or minus. I'm taking a square root, plus or minus. So plus or minus 0.866c. So that's kind of the first step in this problem. What exactly is the speed? And of course, remember, this would be the speed of the meter stick as seen by the primed system. And we were told it's to the left. So we know then that the speed of the meter stick is negative 0.866c. Now, I just realized, and I hope my notation wasn't too confusing, because earlier I put a V, and now I'm using V, but I'm using V for something a little different here. So my apologies if that confused you. So let me just kind of draw a line here, because at first I was talking about our traditional way of listing the velocity of the prime system as seen from the unprimed system, which is really the heart of your question, because let me come back to that before I see how it fits in with this calculation we just did. Because if we have something moving, and in this case it's the meter stick, the person in the S prime system is seeing it move. And I don't want to use the symbol V for that, because I'm using the symbol V for the speed of the prime system moving from the unprimed system. So that's why we switch to a U. And since it's the primed system seeing it, we call that a U prime. So U prime is the velocity of the object that is being moved. And then likewise over here, the unprimed system is looking at the moving meter stick. In fact, that's the question. Determine the speed of the stick as measured by the observers in, both S and S prime. So, okay, so it's both. But from the person in the unprimed system, we were going to call that a U. And so this is the part that I should probably make really clear, because I think this is what your question centered around, is the three different velocities. And so here are the three different velocities. Two of them are the speed of the object. And so the speed of the object is labeled with a U. And if the speed is measured by somebody in the prime system, we call it U prime. But if it's measured by somebody in the unprimed system, we call it U. So that's two of the three. And the third one is what we did first, just how fast are the speeds of the two reference frames. How fast is S prime moving relative to S. Now, I say all that because this calculation we just did, they gave us enough information to figure out how fast the meter stick is moving as seen by the prime system. So even though I called it a V, it really back up here in the problem should be referred to as a U prime. It is the speed of the object as seen by the primed system, and it is moving to the left. So this would be a negative 0.866 C. And again, if I'm reading your comment correctly, this is the heart of the problem for you. What speeds go where?
Yeah, that's what I was really confused with, and that was a good explanation.
Oh, thank you. Yeah, that's why they pay me the big bucks.
Yeah, I totally understand which speeds go where now.
Okay, good. And then, okay, so we've answered half the question where it determines, what is the speed seen by the S prime system here. And so the other half, get myself another page, is to find the U, to find the speed as seen by the unprimed system. Now, without time dilation and length contraction, it would just be U plus a V, or U prime plus a V. But that added factor that we worked out then would be 1 plus U prime V over C prime. I believe. I need to check this myself.
That looks right.
Oh, that's interesting. They put the U prime one in the summary, but not the U one. Oh, let me go back to the text where it's reading. Well, yeah, I'm quite sure that's right. All you have to do is switch the sign. They got the U prime. Oh, there's a U. There it is down there. Okay, good. So it would be equation 3918. All right. So coming back here. Now we can put this in. All right. And so at this point, it's more of a bunch of plugging and chugging. Let me put our first part of that page kind of in the camera's view so we could see. So this would be a negative 0.866 C. Add it to a 0.6 C. And it's like I said, that's kind of the part that to me is the obvious one, because this is what I would have done without time dilation. I would have just said, well, this is a huge speed, but a lot of it is from the 0.6 from this one moving. And so it's really not going all that fast. It'd be just the difference between them. So it'd only be a 0.266 in the negative direction as seen by that person. But because of the time dilation, there's also this factor. And so this would be a negative 0.866 C. And the V would be a positive 0.6 C. And this is the convenience of writing them as a function or a percentage of C, so that that C, those C's cancel off. And then you can even just put a C from the numerator and factor that out. So the numerator would be the negative 0.866 and add to a 0.6. There's the numerator. The denominator would be 1, and I can see this is going to come out to be a minus. I'll just put minus 0.866 times 0.6. All right, so now when I do a quotient, I can go up here and just grab that and divide by that and come up with a negative 0.55 and a 4C. So negative because it's going to the left, and then a 0.55C. Yay. And I suppose I should jump down here to the solution, see what Don did. Oh, good. He got the same thing. Point or negative. Yeah, negative and 0.554 C. And then he did the length contraction. Okay, so nice. All right. Well, unless you guys got other questions on that, I'll switch back over here to the Zoom and look at the chats. All right. Okay, good. All right, Hunter, you're looking at, oh, good, another relativity one. Chapter 39.
Yeah, it's pretty similar to number 2 on the practice exam too. So it's like gonna be a 2 for 1.
Okay, good. Number 59, and I'll put a time here. Let's see, 1029. Okay. And maybe I'll just start the problem. I didn't use much of this page. Maybe I'll try to save a little bit of a tree here and put a chapter 39, number 55. Okay, so I think I called all these up here earlier this morning when I was getting ready. Let's see. It's got to be here. Yeah, nice. Okay, so this is homework. What chapter I'm in? 40. All right, so let me scroll up here to 39, number 55. All right, spaceship 1, or I think that's 1, contains students taking a physics exam, and it approaches the Earth at 0.6 C. And again, probably the hardest thing on all of this is to make sure you read the question carefully. And of course, hopefully your instructor wrote the question carefully, so you know what it's relative to. So that's the key. Everything is relative to something. Okay, and so in this case, what I've read so far would be something like this. So here's planet Earth. What is Florida, and Texas, South America, Maine, and Canada, San Francisco. Not a very good drawing. all these little islands of Canada. All right, here's my terrible planet Earth. Actually, one thing I always find really fascinating about planet Earth is you got, I'll cheat here, North America. But it's easy to forget how far over South America is. If you went from New York south, you end up, okay, now I got to Google a map here. But
I
I'm
know a
pretty
lot of the I know a lot of the maps that they have aren't like super like accurate in terms of scaling. Like I know that there's been a huge problem with like Australia's size relative to other like continents or like
uh,
land masses.
yeah, now that's a little different. That's the fact, if you try to take something that has a spherical shape
Mhm.
and then try to make it go flat, it's like taking an orange pill. If you've ever tried to peel an orange or a tangerine and lay it flat, it doesn't work. And what you end up doing is the stuff near the poles, you end up stretching them out. Yeah, so things like Australia, Canada, Russia, Greenland, they all look disproportionately large.
Yeah.
So anyway, so now I'm on my go. Yeah, so it looks like if I go straight south from New York, I hit the west coast of Chile. Now, South America bulges out a little bit at Ecuador and Peru. So I do kind of hit inland of Peru when I go south of New York. But yeah, directly south of New York, I'm a little bit off of coast of Chile where it curves in, whatever cities may be in Chile. Which I don't think I can pronounce them well, so I better not try. Anyways, sorry, I digress there. But yeah, there's just some weird things on the map that we just don't really think about. That's one of them. Another one is I never think of Reno, Nevada as being further west than LA, but California curves under also.
Oh wow! I used to live up in Carson City for a little while, so that's kind of weird to think about.
All right. Yeah, now I'm going to bring out my map again here. Yeah, if you go directly south of Carson City, There's Carson City. Yeah, right about here. Yeah, you go directly south. You're like Goleta.
That's really weird to think about.
Which is, and Goleta's quite a bit further west than LA.
Yeah, I'm in LA right now, so it's really funny. So
yeah, yeah. So if you're from Carson City and you go to school here in Santa Barbara, you could say you went back east for school.
I like it.
Yeah, I went back east for school. Where'd you go? Santa Barbara.
Yeah, people just look at me crazy.
Yeah, they'll think you didn't learn anything in school. Yeah, so yeah, that's anyways, I digress some more. All right. So back to this problem. All right, so let me emphasize again, because it's crucial in that step when they say that the spaceship containing the students is approaching the Earth at 0.6C relative to what? And they say relative to the Earth. So that's an important piece. So I'm going to put my little spaceship in my picture right here. And maybe, are they going to have a second spaceship? Yeah. So later on, there's a spaceship with professors in it. So, well, so they call it one. So I'll just call it one. Okay. So here's spaceship one. And let me just write down the speed. Let me not decide, whether that is, remember those three speeds we just talked about in the last problem. Is this a V? is this a U or is this a U prime? That's all relative to what you pick as your systems. What is your primed system and what is your unprimed system? So there is no right answer. It could be any of these depending on how you set it up. And so we'll have to make a decision. I don't know if you guys want to or want me to make the decision, but at some point we've got to pick which is our S system, which is our prime, which is our prime system, which is our unprimed system, and which is the moving object. And the good news is it doesn't matter which one you pick, because the speeds are all relative. There is no way to say one is the moving one and one is the stationary one. So keep that in mind.
And the V is the V is the one that we assigned to the moving object, right?
So V is the one between the two reference frames.
Okay, yeah, cool.
And then the two reference frames are each looking at an object. And so the U are the speeds of the object you're looking at.
Okay, cool. Awesome.
Yeah. So let's get to that discussion, which one we want to pick here in just a second, but let's keep reading because we need a third piece of this puzzle. All right. So let's see. While spaceship number 2, containing professors proctoring the exam, move at 0.28 C relative to the Earth directly towards the students. Okay. Now they don't say which side the spaceship is on, and I suppose it doesn't even matter. But then I'm going to put spaceship number 2 right here, and just right next to it, put the number 0.28 C. But again, absolutely important to keep in mind is what speed is that? And they made it very clear as measured from the Earth. Okay. And so both of these speeds are measured from the Earth. Okay. So it says here, if the professors stop the exam after 50 minutes have passed, and again, very important, 50 minutes past where? Because just like distances are relative, and just like velocities are relative, time is relative. And I'll say it again, like we did in the other problem, accepting that speeds are relative is not that surprising. We did that with Newtonian stuff, which meant kinetic energies are relative. We didn't make a big deal out of it. We just kind of accepted that as being true. But these two bizarre consequences, I called the fact that the time is relative bizarre consequence number 1, and length as bizarre consequence number 2. And we won't need it here for this problem, but simultaneity is also messed up. And so that's bizarre consequence number 3. And so those are the consequences you must live with if the speed of light is the same for all the observers. And so nobody really gave it much thought until some of the experiments kind of started showing that. And they were like, whoa, that's weird. And then Einstein was the one who was both brilliant enough and bold enough to say, well, all right, let's just take that the speed of light is the same for all observers, as bizarre as that may sound, but here's the consequences of that. And he was bold enough to, bright enough to figure it out, and then bold enough to say, well, that's what the world must be then. And people thought it was all crazy talk. Yeah. So it became part of the 30 years that shocked physics. It's like, what? Are you sure? This makes any sense? And of course, the big reason is because you don't really see the effect till you get close to the speed of light. So
we can't see that. So
it's a world we don't live in. So of course, it seems weird to us. Yeah. Okay. So with that in mind, here's what I want to do. I want to then go ahead and make some decision. Which, and so we've got our three objects. So one of them is going to be the S system, the unprimed system. The other one's going to be the primed system, and the other one's going to be the moving object.
Yeah.
Keep in mind, it does not matter which one's which.
Okay.
And maybe I'll get a different color here. And so unless you guys have one you want me to pick, I'm just going to take the Earth and call it the unprimed system.
Awesome. Yeah, that makes seems reasonable.
Okay. Again, doesn't matter which we call the primed system, but maybe I'll take the professorship as the prime system. So that would make by default then the spaceship of number one, the students. So the object then that is moving would be the spaceship one. And again, and it's all relative. So I don't mean, want to make it sound like, oh, the Earth isn't moving. It's just we got to pick something in here. And so, all right. So with that in mind, let's see what these symbols were. V is the speed of the S prime system as seen from the unprimed system. So using these definitions, the V would be the speed of the professor's spaceship as seen by the Earth.
Okay.
And they gave me that number as 0.28. And they gave it to me the way I set it up, moving towards the students. Now, we could have set it up on the other way, but the way we set it up, that's to the left. So I'm going to call this a negative 0.28C. Okay. So there's the speed of the professor's spaceship. Okay, so then U is the speed of what I call the object. Okay, so here's the object for the student spaceship as seen by the unprimed system. That's why it doesn't have a prime on it. Okay, so that would be as seen by Earth. And they gave us that number as 0.6. So this would be 0.6C, and it would be a plus 0.6C. Okay. Now, the U prime would be the speed of the student's ship, that's the object, as seen by the prime system, which is the professor's. Now, we don't know that one. We weren't told that one. So we don't know that one. However, just like we did the last problem, if you know any two of those, you can find the third. So we had this equation, U prime equals U, and it's U minus V. Yeah, it must be, U minus V over 1 plus UVC squared. So I got the problem we did earlier from the review, number one. So this was trying to get the U, knowing the U prime and the V. Now we're a little different. We're trying to get the U prime, knowing the U and the V. So if you go through a bunch of math and you move things over, you get a negative sign here. So that's kind of how I remember it, that, okay, these two are nearly the same. Just here you got two plus signs, and here, oh, wait, I messed up. Should be a minus sign down here. when you move things around. Let me check that. Yeah, yeah. So I remember they're both the same sign, both minus on there. Okay. Okay, so we can find this one. I have a feeling we're gonna need it for the question here. So let me put this in. So the U is this, how fast, does the spaceship look like compared to the Earth? So that's the point 6 C. And then minus a negative 0.28 C. And you can kind of see that one come into play here because basically these two speeds are seen by Earth. So you've got the students coming to the Earth at 0.6, and you got the professors going away from the Earth or towards the students at 0.28. So it kind of makes sense that the closing gap between them would be adding the two together. And that's what those two negatives end up doing.
Mm-hmm.
So, and that's what you would have done if you've never included time dilation. But then you have this extra factor down here. And so this would be the 0.6 C and the negative 0.28 C. And you guys can see the math advantage again, that listing things in terms of C's will simplify that for us. So up here, we can factor out AC and just get a number like we did before. So if I do the numerator, 0.6 and the two negatives make a plus 0.8. So the numerator is 88. Now the denominator would be 1. And you can kind of see the two negatives are going to make a positive. It would be 0.6 times 0.28. So there's the denominator. Let me now just finish by grabbing the numerator and dividing it by the denominator and hit enter. And it looks like 0.753 C is the U prime. And maybe I'll just put it right here. Point, and it's positive 0.753 C. So what the professors see is they see the students coming at them really fast. But interesting, it's not just as simple as just adding the two together. It's not 0.88 C. There's also the time dilation going on.
Mm-hmm. Yeah.
All right, so the equation's a little bit harder, but if once you know which symbol goes with it, now it's more plug and chug. So plug it in and chug and get the answer here. Okay, so those are my different speeds and my coordinate system. Now I can focus a little bit more on the problem at hand. So let's see. If the professors stop the exam after 50 minutes, and this is what I was starting to say, 50 minutes measured by what? And so it's 50 minutes as measured by their clock. Now, I suppose the author could be more clear, but I'm going to take that as their clock is with them. Their clock is on their spaceship.
Mm-hmm.
I suppose it could be their clock back on Earth, and it's like, well, this is my clock in my office, but I'm in the spaceship now, but it's still my clock. So I don't think that's what the intent was. The intent was the clock that is with them. All right, because I want to say the same thing for this problem that I did the last problem. Now, the last problem, we were doing proper lengths. But now we're going to do proper times because, again, we have this formula that says the time measured in one reference frame is different than another one. And because of that, we have all these different times we can talk about, just like the length. The lengths are all relative. So we have the way to keep things straight by calling this, and I'll put a big circle, proper time, and then there is then non-proper times. And so there's a lot of non-proper times, just like there's a lot of non-proper lengths, because there's all kinds of different speeds. And of course, the gamma is this factor of the speed between, the proper time and the non-proper you're trying to get. All right. So this brings up a question. When they give me this 50 minutes, is that a proper time? And it says, if the professors stop the exam as 50 minutes unseen from their clock, for what time interval does the exam last as measured by the students and measured by an observer on the earth? Okay, so they have told me there is a clock, okay? And that clock is on the professor's ship. And there is no motion between the professors and their clock. There is motion between the students and that clock. There's also motion from people on Earth and the professor's clock. So the students would be like over here. They would be looking at that clock and recording a non-proper time. The people back on Earth would be something like this. They would be recording a non-proper time. It's the professors on spaceship number 2 that would be measuring the proper time. So we know then this factor right here. And if we then want to find a non-proper time, we just need to know the speed of it. So why don't I'll just go in order. So here's A. They say, what is the time as seen by the students? So I need this gamma factor and then the proper time. We just concluded then that the proper time, and that's what really makes these problems the hardest one, is what is the proper time? Which one is it? You got to read that real carefully here. All right, so the 50 minutes, if the clock is on the professor's ship and the professors say it's 50 minutes, they're telling you the proper time is 50 minutes. So if I want to know what the students would see as measuring back, as looking back, then I need to do this 1 over the square root of 1 minus v squared over c squared, and then times this 50 minutes. And I need to ask the question then, what speed does the clock move compared to the students? And so coming back to what we did here on page 1, that is what we called right here the U prime, the speed of the professors. Well, I guess it's the speed of the students' spaceship as seen by the professors. So the students would see a negative 0.753. It doesn't really matter whether we put a positive or a negative in here, but maybe it might be a little more complete. I did put a negative. But the whole idea here is that there's motion. And again, professors would say the students are going in a positive direction. Of course, the students would say the professors are going in a negative direction. And since that's where the clock is, I'm going to say from the students' perspective, they see a negative speed for the clock. So that's why I'm going to put a negative in there. Okay, So let's get this number. And again, you can see the advantage of lighting things as a fraction of the speed of light. That's why we always do this for relativity. They tend to cancel off. And so down here in the denominator, when I grab my calculator, I'm going to take a 1 minus, and as far as my calculator goes, I'm not going to put in the negative. I'm just going to put 7.753 and square it. And then I'm going to take the square root of that. And then I'm going to take the reciprocal of that. So it looks like my gamma factor is about 1.52. So again, the phrase we like to use is moving clocks run slow. So the students are looking back at the professor's clock, and they're probably happy to see that, hey, that clock's running slow. And if those professors are looking at it and they see 50 minutes, that gives us a lot more time than 50 minutes. They're going to go, hey, all right. And so don't tell them the clock is running slow. We've got this time. All right. So when I multiply this by 50 minutes, I get pretty close to 76 minutes. So that's how the students are going to feel. They're going to be like, oh yeah, their clock's running slow. We got some extra time. Now, somebody back on Earth. So here is part B. And so let's say the time for somebody on Earth watching the same situation. And again, they're going to be looking at the professor's clock, maybe with a telescope or something, and go, okay, that's the 50 minutes, and that's the proper time. That's where there's, we know it's 50 minutes on the proper time, because that's what they said. The professors observed the 50 minutes. But again, the person back on Earth is going to be saying, well, there's a moving clock. And again, moving clocks run slow is the phrase we like to say. So the people back on Earth are going to be saying the same thing, that, hey, your clock is running slow. And realize that the professors are going to give the students more than 50 minutes. However, it won't be the same that the students perceive, because they're moving here. So let's come back to this page 1 here. See, the people on Earth are looking at this clock, which is what the V stood for. Remember, the V stands for the velocity of the prime system as seen by the unprimed system. So the people on Earth are going to say, well, that clock is moving to the left, negative 0.28 c. All right. So let me put that in. 1 over square root of 1 minus, and this will be a c squared down here, but this would be a negative 0.28 c squared. Oh, I guess I didn't need that parentheses. And again, you can see, because he's squared, it doesn't matter whether the professors are moving left or right. But there is a gamma factor here. So grabbing my calculator, let me find that gamma factor. 1 minus 0.28. Actually, and again, I'll just cross out the c squared. 28 squared. Let me take the square root of that, and let me take the reciprocal of that. So the gamma factor is quite a bit smaller. It's still a factor. You might say it's a 4% factor. So the people back on Earth are going to say, hey, your clock's running slow by 4%. So you're going to end up giving them a little bit more than 50 minutes. And you're going to end up giving them about a 52.1 minutes. And that hopefully makes sense because they're not going quite as fast.
Mm-hmm. Yeah.
Now
makes
maybe I better check these answers. It's easy to get these things backwards. 39, 55. Let's see if we in the solutions here agree. So A, they got gamma factor of 1.52, good, which makes 76 minutes. And then B, they got, oh, good, 52.1 minutes. All right, so.
Awesome.
we
Yeah, it
ended-
makes a lot of sense. Like, I think the hardest part is not getting confused about the what you choose for your initial conditions there. So
yeah, and that's probably the best thing I can say is practice these because you've got this little formula that is kind of becomes just a plug and chug, just like these velocity ones. Once you kind of realize what symbol goes with what, and then that's the challenging part.
yeah, awesome. Thank you.
Definition and the primes and unprimes.
Mm-hmm.
All right, good. Yeah, that was a fun one. All right. All right. Let's see. We'll go back to the chat here. Elijah, I have another question about the final. All right. You out there, Elijah?
Yeah, I am.
Okay, good.
So I just saw that I wanted to clarify on what times we're available to take it and how long we have.
Oh, the final?
Yeah.
Okay, let me backtrack one more step. So something I did last semester and going to follow through this semester with the pandemic is I'll make the final optional for you. So if you're doing well, or if you want to invest more time in another class, I'm going to base your grade then on the and again, I don't know if you want to call it 3 exams or 4 exams. I'll just call it 4 exams. But the first one and this one coming up are 50% tests or 50 points. So anyways, if you look at the average of your exams and you do all the homework in lab, you'll get an idea of your score. And if you go back to the email I sent Sunday, I think it went something like this. I think if your average is 85 or above, you're in the A range. Now, if you take the final, then of course the final becomes a percentage. And so there's good stuff and bad stuff about taking the final. So maybe I should put here without final. In fact, why don't I just switch over to that email?
I'm all good. I think I understand like how the points is gonna work, but
okay.
On Neo it says like a certain time to like 12 p.m. and I just have some other finals on Tuesday. So I was just wondering so it's open at like 11, right? I want to say.
Oh, yeah, here's actually going to be the hard part. Here's what I was thinking. I'll use you guys as my springboard. This class normally has 2 sections. There is an 8 to 10 class, and then a 10:30 to 12:30 class. And I believe if you look at the schedule, this class here would have its final on Tuesday, and this class here would have it on Thursday. Now, given that we're online, I've been just kind of grouping you guys all together and putting them at the same time. And here's what I'm thinking. I'm thinking putting the final on the Thursday for two reasons. One is it will give you guys more time to prepare, but two, it'll give me time to grade your test. And then also my sister's funeral is that weekend. So I'm not going to have that much time in the weekend to grade your test. So I'd like to get that grade to you so that, maybe Monday night I'd have everything graded and then you can look at it and decide if you're going to take the final. And that's why I think Thursday would work better. I'd be able to actually tell you Monday night what your grade is. And then you would still have a couple of days to study if you go, okay, I'm going to take that final, or I don't want to give you that grade Monday night. And then if you don't like it, you got to take the final Tuesday morning. That kind of means you better be preparing before Monday. And
Okay.
so that's what I'm thinking. So how
Got
does
it.
Thursday sound?
Thursday, I mean, morning would be perfect for me, but I don't know about everyone else. So
Oh
Yeah.
yeah, and then they gave us some times for it. I think the times on Thursday were 8 to 10. That's what I think I recall.
I think that's what our other exams have been. At.
Yeah. Yeah.
Yeah, I mean, that's good for me. The only thing I was just concerned because Tuesday I have like finals pretty much all day.
Okay. Well, good. So for you, then, and I'm hearing that from a lot of students. I'm hearing a lot of students that they have finals on Tuesday. So that was kind of another reason. I said, well, Thursday's just sounding good all the way around, and give me a time to
Yeah.
get it graded and give you a chance to see your grade by Monday night. Yeah, and then, like I said, more time to study. But also, seems like a lot of finals are on Monday or Tuesday. Maybe that will spread things out for people.
Sweet. Thank you.
All right. Well, and yeah, so you guys are here, so that's why you guys can control the discussion.
Yeah, if I take the final Thursday, I think would work really well.
Yeah. Okay. All right. Well, yeah, I'm not hearing Tuesday as a viable option. So good. Yeah. And if they're, so I think that's what I'll decide on Sunday when I write this out. I'll explain that. Okay. If you choose to take the final, it'll be on Thursday, and then if I have to work with individual people because of conflict, that's fine. I'll do that too.
Sounds good. Thank you.
Uh-huh. All right, let me go back here to the chat. No, I don't see anything in the chat. All right. Means you guys got it all nailed. You're good to go. Hey, so I'll ask you guys another question too then. Next week, your half exam is coming up for Thursday. So I don't think a Friday Zoom would be very useful. Except for those who are going on to take the final. But I think that's going to be a small number. So anyway, should I do a Zoom on Wednesday? Should I do a Zoom on Tuesday?
If you could do one on Tuesday, that'd be great for me because I have work at 9 a.m. on Wednesday, so I wouldn't be able to attend on the Wednesday.
Okay.
Yeah, I also have classes on Wednesday too, so
Oh,
I'd only be able to go to like one session
okay. Both of you are
If
thinking
possible.
Tuesday.
if possible.
And I lean towards 2 days in advance so that,
Mhm.
one day we can kind of talk about it, and that gives you a whole nother day to digest it and get ready for it. So I'm thinking next week's Zoom ought to be Tuesday, since by Friday you've already taken the exam. Okay. Yeah, maybe should make a note to myself here for Friday. So I need to make sure this Sunday I kind of explain Zoom time and Well, I got to explain the exam, but I should also explain then more about final exam. A lot of information this Sunday got put together for you. All right. All right, Hunter. Looks like in my chit chat you threw another question at me. Okay. All right, so let's try number. Let's pick up right here. What is this? Chapter 39. Okay, more relativity. Number 56.
Yeah, it's one of the review problems there.
56. Time is 11:11. Oh, and you said it says review.
Yeah, and
But-
it kind of looks like one of the ones that are on the pre-exam too, or the practice exam too.
Okay.
Yeah.
All right. Well, let's give this one a try here. And again, as we've seen on the other two we've done here, things are all relative. And probably the hardest part is keeping track of that relativism and what the symbols mean here. So let's give this one a try here. Here it says an electron is traveling through water at a speed 10% faster than the speed of the light in water. Oh, now this always confuses students a little bit. We should be real careful. We talk about nothing can go faster than the speed of light. What we really should say is speed of light in a vacuum. All right. So, in fact, the symbol C for the speed of light is unfortunate because there's just something part of nature that this is the maximum speed. I think it would have a better name called the maximum speed or something, not just the speed of light. Because light was just the first thing that us humans knew about that went at this maximum speed. We had no idea that, say, other massless particles like gluons or gravitons would all go the same speed. We also had no idea that this gamma factor and comes into play, which is a connection, and relativity comes into play, which is how fast are you going in proportion to this maximum speed. So this maximum speed is something far more richer and important than just the speed of light. But nonetheless, we've got this C that we often call speed of light, which isn't a good name, but we should at least go on to say speed of light in a vacuum. Because when light does slow down in the water, that does not change the other important part of this C. It does not change the gamma factor. So even though the light slowed down, it doesn't really affect, say, neutrinos or gravitons or gluons. So it's misleading. And so that's why then you could actually have an object like here, an electron, going faster than the speed of light in water. So let me start with that. So they're saying the speed of light, V, is 10% faster. So I'm going to go 10% faster. So 1.1 times speed of light in water. And maybe this is the part where the author has review come from, because we know that the speed of light in water, so we got to go back a couple of chapters, that's why it says review, to our optics. We know that the speed of light would be C divided by the index of refraction of water. So going back to chapter 35, or if you remember it, the index for water was this 4/3, this 1.33. All right. So that's why I'm sure the author put review. But more than that, it's just a good problem because it is trying to clarify and just that, hey, you can go faster than the speed of light in water. Nobody said you can't go faster than the speed of light in water. The physics says you can't go faster than the speed of light in a vacuum. You can't go faster than this maximum speed. All right. 1.1 divided by 1.33 then is 82.7% the speed of light. So that's kind of where I would start this problem with, well, how fast is this electron going compared to the maximum speed of the universe or the speed of light in a vacuum? And that's the important piece because that's where gamma comes in. How does it compare to this maximum speed limit? Okay, so there's the first part. Let me just read it here. 10% faster than the speed of light in water. Determine the electrons, and then A, its total energy, B, its kinetic energy, and C, its momentum. All right, so again, maybe just a little more plug and chug here, depending on how you want to do this. But one of the many great discoveries here was that the total mass includes what we call now the mass energy of it, the rest mass energy. So if you subtract off 1 mc squared, you get just the kinetic. And so these are our two pieces. This A, what's the total energy? And then B, what's its kinetic energy? And then we'll get into momentum here next, because there's a couple ways we could do momentum. So each of these depend upon this gamma factor. So coming back up to here, gamma is 1 divided by the square root of 1 minus, and so here's the speed, 0.827 c, and we'll square it. And we have to divide it by c squared. And like the other problems we were doing, this is kind of nice to write it as a fraction of the speed of light. So that cancels off. It makes it a little easier to calculate this important factor, which we call the gamma factor. Okay, so 1 minus 0.827 squared, taking the square roots of that and the reciprocal, and gamma is about 78% greater than 1. So if we go slow, gamma is a factor of 1. And that's why all of the physics we've learned up to this point was what we call Newtonian physics, because nobody knew about these length contractions and time dilations. And so gamma always came out to be 1. And so you had kind of different looking equations. All right. So now I can come back up here and write this gamma factor is 1.78. And here I have an interesting choice, this mc squared. And if we wanted to do it in joules, we could, because we know the mass in kilograms, and maybe I'll do that also. But just like it's really convenient to write the speed as a fraction of the speed of light, it's really kind of nice to write the mass of an electron not in kilograms, but in some weird units you might not have ever seen. They're units of energy in electron volts, mega electron volts, divided by c squared. So that when you multiply by c squared, the c squareds go away and you have it in units of mega electron volts. And so just like you saw me down here, the convenience of writing speeds in terms of the fraction of the speed of light, it is convenient to write mass in terms of this weird unit that might be new to you. So I'm going to do both. But if I look it up in these weird units, it's 0.511 MeV over c squared.
And that's just for one electron.
And that's one electron, yeah.
Okay.
And then, like I said, the neat thing about it is the c squareds would cancel off. And so now I can just take my gamma factor and multiply it by 0.511 and get 0.909 MeVs, which stands for mega electron volts. Hang on, where's my dog barking here? Hey. Okay. Crazy dog. All right. All right. So mega electron volts. Hang on. There we go. Okay, well, it looks like I got a package delivered. So, good old Amazon delivery. All right. Okay. So now, and by the way, before I do B, then I think it might be kind of fun to just see this because, again, one of the things you're being exposed to are these new units, and they're really convenient. They're just really weird looking at first. And so let me do that again. Let me just say that the energy would be gamma mc squared. Here's the gamma factor, 1.78. You're probably more used to looking up the mass of the electron in kilograms. And if I do that, it's 9.11 times 10 to the negative 31 kilograms. And C is the 3 times 10 to the 8th meters per second, and square that. So rightfully so, I bet most of you would have done this problem because in these units, and that all comes out to be joules, because there's your kilogram, your meters squared, and your seconds squared. So if I did this in joules, I would get 1.78 times 9.11 times 10 to the negative 31. And that's, as you said earlier, Hunter, that's one electron. And that's pretty small. You know, they are pretty small. Then times 3 times 10 to the 8th, and that whole quantity squared. And so in terms of joules, this would be 1.46 times 10 to the negative 13 joules. Now, just to show you this comes out to be the same, what is called an electron volt is a unit of energy. It's a small unit of energy. It's the same as 1.602 times 10 to the negative 19 joules. And it's a convenient unit of energy for small energy amounts. So when we're dealing with small objects like electrons, to use joules is just kind of overkill. I mean, that was great in Physics 121 when we're working with a car and we say, what's the kinetic energy of a car or or even in our electronics, and we got a light bulb and we go, how much energy did it use all day long? But when you got little tiny things like electrons, it's kind of nice to have another unit. And we call it an electron volt because it is actually derived from the idea if you took one electron and applied a voltage of 1 volt to it, how much energy would it get? And it would get this much in joules, 1.602 times 10 to the negative 19. So we call that much energy 1 electron volt. All right, so if I do this and convert the joules into electron volt, 1.602 times 10 to the negative 19, I get 911, so 911,000 electron volts, which if I move the decimal 6 places, that's 0.911 mega electron volts. And that's essentially what I got here when I just looked up the mass in mega electron volts.
Hmm.
So I think part of this is just weird units. In fact, I know I still have to do B and C, but I'm kind of curious here then, what units did the author use in the answer? Yeah, and so he put it in like this. And I'm glad he did, but I also am glad I did both, just to kind of show you that, you know, hey, this is not as bizarre as it looked. It's just new to you. And so, but it's really convenient to have the C squareds cancel out, just like I've been showing you for the last hour and a half here, how the C's cancel off there. And so it's a nice unit. So you get down to these little tiny things and you get into nuclear physics, they just kind of have their own world of their own units. It's not the kind of standard SI units for you would see with boats and planes and cars and automobiles. It's, yeah. Okay, so now with that in mind, I can go to B. And of course, then the neat thing about the discovery of all of this was that rest mass is part of the energy. So if you take the total energy, which would be this first factor, gamma mc squared, and you subtract off 1 mc squared, in other words, you subtract off the part that has to do with its rest mass, what's left over is the kinetic energy. And I'm pretty sure what's neat about this problem is you don't do this 1/2 mv squared. That was the big lesson. This 1/2 mv squared, which you guys learned early on back in Physics 121, and you've been using constantly until you got to this chapter, was really an equation that I tried to show you with a Taylor expansion in the video lecture. It's only valid if you are going kind of slow compared to the speed of light. So 1/2 mv squared can be thrown away now, although it's pretty darn accurate if you're under 10% the speed of light, and very seldom do objects go more than 10% the speed of light. Our electrons can do that pretty regularly, and on this problem, they're having electrons going 82% the speed of light, or closer to 83% the speed of light. So for this problem, to use 1/2 mv squared would give us a very wrong number. But anything, most other things like a train, you know, even a rocket ship, you know, I know SpaceX launched this morning, and it was like, okay, neat. And then, wow, it's going really fast, 17,000 miles an hour. Yeah, big deal. Way under 10% the speed of light. So as you're engineering the spaceship, calculating its kinetic energy as 1/2 mv squared is certainly fine. But for electrons, that's not going to work well. So for this problem, if you used 1/2 mv squared, you kind of missed the point and it would be wrong and you get a very wrong number. Okay, so let me take then the gamma factor, which we said was 1.78, and subtract off the 1. And as far as the MC squared, let me do these new units that I exposed you to. And so let me write the mass of the electron as 0.511 MeVs, mega electron volts per C squared. That way, when I multiply it by C squared, they can just cancel and I don't have to really even mess with it. It makes it easy.
Mhm.
And that's, again, what I'm trying to show you with these bizarre units. I mean, obviously, we don't want to have bizarre units and make things harder. That's not a game. That's a lose-lose proposition. But in this one, we've got bizarre units, which is kind of a lose, but they make it really easy, and that's a gain. And the gain is more than the loss. So you begin to just get used to these different units.
Mhm.
All right, so 0.78 times 0.511. Oh, you know what? Did I write down the time I started this one? Yeah, good. All right. And so this is then 0.398 MeVCs, which we can convert to joules if we want to, but I don't think we want to. So I'm saying, nah, don't mess with it. And still got on my computer screen here the answer from your author, and he just sticks in MEVs. So, all right, so we'll take that one. And then C, I kind of held off on C because we had two ways to do that. One of them is to realize that E squared is MC squared squared plus PC squared. There's the momentum. And the other one was just to realize that it would be gamma MV. And to me, it looks like this might be an easier way to go. Although I'm looking at the solutions, it looked like the answer the author did was this. So I'm gonna go this direction and see if I can get the same thing. Now remember the gamma factor we did earlier. What did I do with the gamma factor? Here it is on page 1.78. So 1.78. And again, watch these weird units. But remember the mass was 0.511 MeV over C squared. Okay, that's weird looking. Okay, but remember, now we're going to multiply by the speed. And so this speed is 0.827 C. And let me give myself a little bit of room here. I'll still go to another page, but what's nice then is at least one of the C's cancel off. And you're left with MEV over C. And so MEVs over C's would be nice units for momentum.
Okay.
So for energies, we have MEVs. For mass, we have MEVs over C squared. And for momentum, we have MEV over C. In these weird units. Now, again, you can convert this to joule, you can convert this to kilograms, and you can convert this to kilogram meter per second.
Okay.
And those are the ones that you're more used to. And I probably will, when I'm all done, is switch this over to what you're used to, which is kilogram meter per second, just to kind of show you it's the same thing. But it makes it really nice that if you just leave it in MEVCs, you can just continue to use this little equation here. And so 1.78 times 0.511 times 0.827, and we are looking at 0.752 MEVCs.
Mhm.
And your author, okay, writes in both. He does this. He does exactly what I just did, although he uses this formula to get there. So he uses this formula and then writes the answer, and he gets the same answer. It doesn't matter which way you go. And he gets 0.752 MEVs over Cs. But he doesn't stop there. He does switch it to the units you probably are more comfortable with. So I'll do that too, which I find kind of interesting because he didn't do that over here. He left it as 0.909 MEVs. He did not switch it to what we did, 1.46 times 10 to the minus 13 joules. So he didn't do that in part A, but he does do it in part C. All right. But I think it's best that I did it in A, and I'll do it here in C. So let's switch it to the units that you feel more comfortable with. And hopefully that will help you as you're transitioning from your units that you're used to to these new units that are often used in things like particle physics and nuclear physics when you're working with these little things. So let me take the momentum as 0.752 MEV over C. And now let me do the conversion. So 0.752. I'll start with the M. The M is mega, so that's times 10 to the 6th. Let me, well, maybe I should just put EV over C first. Maybe I should do that. All right, so there's the M EV over C. Now to get rid of the EV, as I said earlier, how many joules are in one EV? And so I'll say it again. The reason we use the symbol EV is this was the early scientists saying if you took one electron and then you shot it with a voltage, and so you attracted to a positive plate, and that positive plate was at 1 volt, how much energy would it get? So they called it an electron volt. All right. And that electron volt, then, by definition of one electron being accelerated by 1 volt, is in terms of joules, 1.602 times 10 to the minus 19 joules. So that would convert it to joules. And if you replace C with 3 times 10 to the 8th meters per second, and I'll worry about the numbers in just a moment, but you'll see here that I have down in the bottom meters per second, and in the top I have a joule, which remember is a kilogram times a meter squared over a second squared. So this meters per second in the denominator is going to cancel with 1 each in the numerator, leaving me with the units that you probably feel more comfortable with for momentum, which is a kilogram times a meter per second. All right, so these do come out to be the appropriate units. And so, like I said, it takes a little getting used to, but MEV over C is now then a unit, MEV over C for momentum, just like MEV over C squared is a unit for mass. That's weird. This isn't so bad because MEV, I mean, the definition of EV is how much energy does it take one, so to see it as a unit of energy, that's not bad because you're really, the definition of an EV is how much energy do you give one electron when you accelerate it by 1 volt? I mean, just the question, how much energy? So that's easy to recognize. It's a unit of energy. But then dividing it by C squared is mass, or just dividing it by 1C is momentum. It's kind of new. All right. So to finish this problem, and if you guys have another question or if it should be break time, we'll go here and say, all right, let's take this number. So this is the 0.752 times 10 to the 6th. And if I divide that then by 3 times 10 to the 8th, and then multiply that by 1.602 times 10 to the negative 19, I get 4.0, and I'll round it up to a 2 times 10 to the negative 22. Again, you can see the numbers are so small, it's just really nice to have other units that aren't for the big things we learned in physics 121. You know, these units for momentum are great when you're dealing with a bike. They're not so great when you're dealing with these little electrons. They're just tiny. But let me check, what did your author get? He got 4.01 times 10 to the negative 22 and units of kilogram meters per second. Yay. Oh, wait, there's a part D. I see that in the solutions here, but I don't recall reading it. Let me switch back here.
I'm guessing this one has to do with our diffraction or whatever.
Yeah, okay.
Practical light.
Well, it actually, I think it has more to do with going all the way back to, where do we get Doppler effect and shock wave?
That was the first section, right?
Yeah, it was the first section with waves. So actually, I had mentioned that maybe this was labeled as a review because we had this speed of light, and that's true. That was a review back to the optics. But I would say this is even a deeper review. This is going back to, if you remember, if you had an object that was moving, and at first, if it was moving at a speed less than the speed of the wave, usually we did sound waves with this, that the waves would kind of crunch together, but because you're moving slower than the speed of the waves would move out. And so somebody standing over here would then hear the sound crunch together. They would hear a higher frequency. And then the person who explained that was Doppler, and so we call this the Doppler effect. If you were on this side, the waves would be spread out because you're moving away from you. What got even more interesting is, what if you went faster than the speed of the wave? And so something like that, maybe it started here, then in 1 second moved to here, then moved to here, and then finally was here. And if it moves faster than the speed of the wave, so take a wave that started here moving out, I'll just put it off at an angle, it would not move as far out as this moved forward. So this would be maybe right here. Now this would be a second after this one, so it would be maybe right here, and this would make a wave right here. And if you did all the spots in between, you get, and it's easy to see this with water waves, as you call it a bow wave, if it's a boat, and water waves are so slow that it's easy to see a boat going faster than water waves. But you get this kind of this V-shaped pattern, and this is then our shock wave. You get the same thing if you go faster than the speed of sound. It's just not often that things go faster than the speed of sound, but some things do. But what you get is the superpositioning. So you don't hear the individual sound that the object makes, but you get a large compression of air if this is sound waves, or if this is water waves, you get a big bulge of water right here. So you would call it a bow wave. But anything that goes faster than the speed of the wave itself would make this shock wave. It would make this high intensity here. And that's what's interesting about this problem, is because remember, we are going 10% faster than the speed of light. Now, let me say it again, 10% faster than the speed of light in the water, not 10% faster than the speed of light in a vacuum. Mm-hmm. So this electron would actually produce light waves. Mm-hmm. that would make a shock wave, and it would make this really intense flash of light.
Would it actually cause like a physical disruption as well, or like because it's like would be interacting with the water particles too, or?
Yeah. So it takes energy.
Okay.
So just like a bullet moving through the air has to give some of its energy to the shock wave,
Mhm.
or an airplane has to give its energy to the shock wave. This electron has to give some of its energy to this flash of light it's going to produce.
Okay. Cool.
And it's a Russian name. I think they have it later on in this. Let's find the angle between the shock wave and the electron's direction of motion around the core of nuclear reactors shielded by a large pool of water. Oh, there it is. How do you pronounce that?
Cherenkov?
Cherenkov?
Yeah.
Okay.
I've actually seen the blue glow before. I just didn't really know much about what it was.
Okay. So this Cherenkov radiation, which is what we call it now, was explained by the Russians. And so when they built the reactors and cooled it with water, they saw this blue-green glow, and nobody kind of understood what was going on. And the Russians figured it out, or this Russian scientist, Cherenkov, figured it out. So now we call it Cherenkov radiation, and it's kind of this blue-green glow from these electrons, and they only show up when you have these particles going faster than the speed of light in water.
Mhm.
Yeah.
Okay.
So, anyways, back to this problem here is then, and you might need to go back to chapter. I want to say this was 18, but it could have been 17. Probably was 17. So in 17 and 18, I'm pretty sure we did Doppler and shock in 17. So I'm going to say 17. We did this, and we said this. We said that if you drew a line out here, and this goes out, say, perpendicular. My drawing didn't show it real well, but that'd be a right angle. Then this wedge shape would have an angle theta. Oh, actually, I think we called the whole angle theta. But let me call that. Let me look. 17. We call the whole angle or half the angle? Okay, so here's shock wave. It is 17. Nope. It is the half angle. Okay. So he calls this half angle theta. Okay, so the whole wedge would be 2 theta. So if this was a boat going through water and you were up in a helicopter looking down, you would see a wake and you would say would be 2 theta. But here's how you get it. You can kind of see it, the sine of theta. And so if you've got a right triangle here, this would be the opposite. So this would be how far did the wave travel? So this would be the velocity of the wave multiplied by some time frame that it took you to get to here. Then, of course, down here, this would be the hypotenuse. And so this would be the velocity of your source of the wave multiplied by that same time frame. So the time cancels off. And so you get that angle by taking the ratio of their speeds. So the speed of the wave for us would be c divided by n. So that's the speed of light in the water. And the speed of the source, remember, we said was 10% greater than the speed in the water. And so I'm going to write it in terms of the speed of the water so I can cancel that off. So that's 1 over 1.1. And so now, squeeze it in here, theta would equal the inverse sine of 1 divided by 1.1. Oh, and I think I'm in degrees. Okay, good, I am. So this would be a 65.4 degrees. So if you could catch on video this thing going through, you would see kind of this wake, and it'd be a little bit wider than my drawing, but it would come through here. And so it's going just a little bit over speed. So probably a better picture. This would be the wake or the shock wave. I shouldn't call it a wake, since wake is specifically for water shock waves, but there would be the shock wave of light. Go out like that.
Awesome. Cool. It makes a lot more sense. Yeah, I forgot about some of the older stuff, so that was definitely good. I need to get back on top of that.
You're not supposed to tell your teacher that.
Oh, whoops, my bad.
Yeah, I forgot the earlier stuff. The class was so exciting.
No, it is. It's just a lot.
Yeah, I understand. I
Yeah.
completely get it.
Yeah, but thanks. Appreciate it.
All right. I got some good ones here. But let me ask, would it be okay if we took a break? Are you going to be back around? Let's see who asked this. Ryan and Ed.
I'll be around. I'll be around.
Okay. Ryan, you going to be around? Or do you got to go to class? No. Kind of silhouetted in the dark there, but I think,
He's there
Hello?
as well. You might just be down.
yeah.
Uh,
I'm gonna write it down. Okay, so let me write down those two. So he's asking about number 52. And Ed, you're asking, about pushing the wheel over the curb. Oh, good. I want to go through that one. I think I made a video of that one too, didn't I?
Oh,
But
If you did, I can go back and check it. It was just really just the setting up of it. I couldn't quite figure out the physics of what was going on. So I can, if there's a video, I can go back and check that.
yeah, check it. I think I did it last week. Check
Okay.
that out.
Real good. Hey, I just wanted to tell you how sorry, you've probably been over this, but how sorry I am to hear about your sister. I lost my big sister 30 years ago, and it was a real, it's not fun.
Yeah.
So I'm
Hey,
really, really sorry.
yeah. Thanks. Yeah.
Thank you.
Just bad. Yeah. Yeah, you bet. All right. Well, so I'm going to write that one down though, just in case. So I'm going to ask you when we come back, but if you want to take some time in the break, check. I think it was the Zoom, but I'm not 100% sure.
Okay, I'll find it. Thank you.
All right. All right, guys, let's take a little break and we'll come back and do yours, Ryan, okay?